Thank you, Zeke. You have to scoot now, baby doll. Okay, here is what I hope will be a brief conversation about the momentum issue from the collision question. So in this scenario, there's a stationary ball and a ball smacks into it, and the ball that was stationary goes on to smack into a wall, rebounds off the wall, and more things happen. So in the situation where the ball has smacked into the wall and then it comes back away from the wall, those arrows are just meant to show directions of motion. We write a restitution equation, but we don't write a momentum equation. And I want to talk about why that is. I don't think that what the book said was very helpful. It said, since the impact is external, momentum is not conserved. I think what they're trying to say is, if you have a closed system, then momentum is conserved. So a closed, whoops, right, closed so you can read it. A closed system means all the bits involved are accounted for in your setup. So a closed system, then you conserve momentum. But if you have forces acting externally from your system, then momentum will not be conserved. And so I think what the book was trying to say is, because this wall is stationary and the ball smacks into it and rebounds, there are forces holding the wall stationary. The wall doesn't slide, the wall doesn't fall over, the wall has absolutely zero change to it in our story. And so there's forces happening outside of our picture that make the wall do that. And so therefore momentum is not conserved. And that makes semi-sense to me. I have a bit of a problem with that, because to me, well, but the ball hits the wall and the wall pushes back on the ball, and I don't know. It's all kind of weird to me to think of it that way. If you see it that way, that there's external forces involved with the wall not moving, and therefore it's not a closed system, therefore we don't write a conservation of momentum equation. If that makes sense to you, great, go on your merry way. I needed to think of it more like this, that, okay, so let's let capital M be the mass of the wall and little m be the mass of our balls and walls. Okay, and the initial velocity of, I'll say sphere, of our sphere heading toward the wall will be u, and the rebound velocity will be v, and I'll take this as positive and to the left is negative, so I know that v is a negative number. Okay, so, and I know that the wall is stationary throughout. So if you do momentum before, so our little sphere's mass times its initial velocity, and the mass of the wall times its initial velocity, well, that should equal the final stuff, right? Now, this is where it gets, this is where I got hung up on it, okay? That you're going to have some, I'll do a capital V for the wall's velocity after the ball smacks into it. Now, we run into trouble if we say, well, the wall doesn't move, so its velocity is 0. And then you have mu equals mv, u equals v, and that's not true, because I mean, even if it's a perfectly elastic collision, that's a positive number, and coming back it's a negative number, so there's no way that can be true, and I got really upset about that. And I suppose if you say, okay, well, the wall not moving at all means there's external forces that aren't being accounted for in all the system of velocities and mass, so momentum is not conserved, and maybe that's a way it makes sense. But the following made a lot more sense to me. Let's think about this wall being connected to the ground, to the building to the continent, to the entire Earth that is sitting on. You can think of this wall as being just like a little projection of the whole planet Earth that the ball smacks into. Because I really, really want to keep the idea that, you know, if you're on a raft, here's my beautiful artwork. If you're on a raft and you step off this way, you have to push on. You're I don't know. You're going to jump into the water. You're going to jump on. I don't know. You're getting off the raft. So you push your back foot off so you can go this way, but it's going to send the raft that way. We've all, like, you know, flailed in the pool trying to mess about with stuff like this. So, you know, things one way affect the other way, and I just can't find peace with the wall doesn't move at all in this story. I really want a story for why I can't use this momentum equation. And so, okay, so the ball smacks into Earth this way, the ball moves back to the left, and Earth moves to the right. And, you know, I remember a physics teacher telling me once, you know, like, if you, because, you know, we were like, well, okay, so, you know, you jump one way and the raft goes the other way. Does that mean if you jump on the surface of the Earth, you have to push off the Earth to launch into the air? So if you go up, shouldn't the Earth go down? And the answer is yeah. Yeah, it should. And yeah, it does. I mean, okay, so there might be a whole bunch of other forces. There are a whole bunch of other forces going on all at the same time. But the theoretical model allows for it, that, yeah, you go up and the Earth goes down. But the thing is that the Earth is so fantastically massive, and your little mass velocity jump is so tiny that the resulting velocity on the big massive Earth is fantastically small. But it's not zero, and that made me feel better. I don't care how small it is. I just want to know that it's there. So where does this help us in our momentum equation? Well, we've got on the left, we've got our little sphere times its initial velocity is our little sphere times its final velocity plus giant mass of the Earth and some velocity that's going to be weenie. And if you know the mass of the Earth is something like 6 times 10 to the 24 kilograms or something fantastically big. If we know the approach velocity and the ball's ricochet velocity, we can work out Earth's resulting velocity. And you're going to get something stupid on the order of 10 to the minus 24 meters per second. It's stupid tiny, but it's there and you can calculate it. But you got to know that number. And so in our story, we didn't know the mass of the wall or whether we wanted to take the whole Earth or what the deal was. And we didn't know our final velocity after hitting the wall. So if you don't know that and you don't know that, and there's, what do you do with that? There's too many unknowns and the equation becomes unusable. I was about to say unusual. Maybe it is a bit unusual. It becomes unusable. And it's unhelpful. So we just, in a sense, we just, you know, ignore it and walk away. And that made me feel a little bit better about the whole affair here. I think there really is something in saying, do you have a closed system? If you do, then you conserve momentum. If it's not closed, then you don't conserve momentum. And I think, you know, we do rely on that sometimes, I guess, in fancier two-dimensional problems. So perhaps we should, you know, make a really big fuss about that. I couldn't make my peace with this story, so I had to go through that. I talked to Colin about it, and Colin said, okay, if you rearrange the variables a little bit, so we subtract the sphere's bits, and that's, you can think of it as like a really massive wall or the whole Earth or whatever. Maybe we're on Mars, I don't know. And you know, divide by big M, maybe factorize if you feel like it. His argument was, as the mass of whatever you're smacking into, as the mass of whatever you're smacking into gets fantastically big, then the resulting velocity gets really, 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 really close to zero. And that makes sense. I can understand inverse relationships. That's okay. But the idea of this ran into trouble for me, Sophie, because if you send m off to infinity, you're sending v to zero, then you've got kind of a situation of infinity times zero, which is a really ugly place to be. And, you know, limit theory has all kinds of nightmares and headaches with things like this, for how to sort out the resulting limit of that kind of affair. You know, does that go to zero fast enough to drag the wild numbers getting away from you, or what? I don't know. It's horrible. So that helped me understand that the bigger the mass, the less the resulting velocity. But we know this from, you know, just dinking around in real life. You know, you collide with a little kid, the kid goes flying. You collide with a big chunky 6-foot sumo wrestler, he doesn't go flying. We know this. So I'm not sure I can say anything that's much more useful, except I wanted to show you something from the textbook, just again about okay, this is okay, that's the ball smacking into the wall, and a little bit about conservation of momentum and stuff. I just wanted to make one more mention of momentum and directions and things. No, I don't, because it doesn't make sense in this video. Sorry, that's it. That's it. If you still can't sleep, let me know. All right, thanks for watching.